Good afternoon. Thank you all for attending another one of these Swift overview uh, sessions. Um, I hope everyone can see my screen, uh, and we'll go ahead and get started. I think everyone's here. Okay, so let's see. Last week we did a number of things. We ended with arrays. We were trying to get through both arrays and dictionaries, the two collection types in Swift, and and we didn't get through all of it. We didn't have time to get through dictionaries. So we're going to pick up there today, and then we're going to go into functions, closures, and enums. I had originally intended for us to try and also do structs and classes, but then I realized there were actually a number of topics related to functions we still needed to go over in order to understand closures. So this will be the topics for today. Most of you, I think, already know who I am. My name is Bennett Smith. My business partner's name is Terry Tucker. We run a small company called Focal Shift. We do contract software development for iOS. And just like everyone else, we're busy learning Swift. So these are a way for us to be learning as we go along and also to help other people learn the language as well. Like I mentioned last week, we did control flow, strings, and collections. And I recorded the session and put it up on YouTube. There is a YouTube channel that you should all be able to get access to through the link here, or I also posted the link into the Meetup group, so you can find it there as well. And if you are someone who likes learning from these videos, please send Terry or I an email. Let us know how it's working out. I really, this is the first time we've really recorded anything, and we don't know if they're valuable or not. So I'd love to hear some feedback on that. Okay, so today, like I said, control flows, functions, just basically some more advanced topics around functions, and then closures and enums. So as with the previous weeks, all of the files I'm going to go through today are up on GitHub in our Swift Intro Playgrounds repo. So feel free to grab those and follow along, or grab them later and play with them in Xcode yourself. Everything's still being done in Xcode 6 Beta 2 right now. Okay, so let's pick up with dictionaries now. Swift provides a dictionary type that is pretty powerful, but it is different than the Objective-C dictionary. In the Objective-C dictionary, you can have values of any type. So a dictionary has keys and associated values. In Objective-C, we can store a mix of different value types in the dictionary. In Swift, we don't have that capability. We have to store everything of the same type. So it's a strongly typed collection. We specify the type of the key. We also specify the type of the value. The simplest form would be something like what you see here on line 109, where we're declaring a dictionary with a key of type string and a value of type double. And inside this initializer syntax here in parentheses, what we are doing is we are telling Swift that we'd like it to initially allocate enough space in memory to store 10 potential key value pairs. So it basically allocates one chunk of memory for that. If we wanted to create a literal dictionary, we do that using a syntax similar to the array syntax. So we sort of group everything inside square brackets. The difference here, though, is we define the key that we'd like to store, and then a colon separating that value, separating that from the value that we're going to store. So this represents one element in the dictionary, right? So this particular dictionary literal here has two elements in it. And we can see that if we quick look it over here, you can see that there are two elements in here. Each of them have a key and they each have a value associated with them. Once you have a dictionary, so the next line here, we're creating a variable. The variable's name is airports, and its type is a dictionary storing a string as the key and a string as the value. And we're storing our two airports in there for Tokyo and Dublin. And once we've got this variable, then one of the things we can do is we can ask it how many key value pairs are in it with this property called count, and you can see right now there are two. With a dictionary, one of the things we're going to want to do is we're going to want to add additional key value pairs to it over time. And the syntax for that is fairly straightforward. Inside square brackets, we would put the new key name that we want. So here we want to store Oakland Airport. So the key is Oak, and then we assign the value Oakland to it. And so once that's been done, then airports contains 3 key value pairs. If we wanted to set the value using a different syntax, it's going to do the same thing, but we can use this update value method to add a new key value pair as well. And so this is in kind of a reverse syntax. So the first element here is the value, and then it says for key, and the second parameter here is the actual key name. So at this point, airports should contain 4 key value pairs, and you can see that it does right here. If we want to work with an element in a dictionary, one of the challenges that we're going to face is we don't always know whether or not that particular key we're looking for actually exists. There is a syntax in Swift for something called an optional, and using an if conditional, you can do something that's called an if-let statement, which is what we're seeing right here. And so what this line is basically doing is it's asking us to go look in the airports dictionary for something with a key of den and assign the value of it to a variable called airport name. Now, this syntax will only actually perform this assignment if there is an element in the dictionary with a key of den. If there is no element in the dictionary with the key of den, then this conditional statement here will evaluate to false, and we will hit this else clause here. So that makes it, that means it's very straightforward to basically go test and retrieve from the dictionary in one statement. And we're guaranteed that by the time we get inside this if block here, we've actually successfully assigned the value from the Denver key into the variable airport name. Now we can see that in our dictionary at the moment, Denver doesn't exist. So what should happen is that should print out airport not found. And right here, you can see that it actually does print out airport not found in the console. So if we try that same thing, but we try it for an airport where we know that the key is found, you can see this block here. So we're doing another if-let statement, and we're looking up SFO, and we get the airport name, and it is found. So you can see here it says found SFO. All right, so that's the if-let statement. Now, what that's doing is that's basically letting us evaluate and do what's called unwrap an optional variable in Swift. And we'll talk more about unwrapping and optionals as we go along. So, okay, so we've seen how to add things to a dictionary and how to get values out of a dictionary. The next thing here is how do we actually remove things from a dictionary that we no longer want to be stored in there. And the simplest way to do that is to just use the same syntax we use to add something. We say airports square bracket and the key name equals, and we assign it a nil value. And that basically removes that one key value pair from the dictionary. It takes care of all the memory deallocation and everything. It's just a done deal. An alternative syntax for that is to use a method called remove a value for key and provide a key. So here we've basically removed both SFO and Oakland. And so if we look at airports again, you can see now that the count is back to just 2. Okay, so that's basically removing something. Another common thing that we'll want to do with the dictionary is we'll want to just walk through all of the elements in the dictionary. In Objective-C, it was common for people to iterate over a property of a dictionary called all keys, and then from that dictionary, use the key values to go fetch, use the keys to go fetch the values out of a dictionary. In Swift, since we have tuples, there's no real need to do anything like that. We can actually iterate the keys and the values together. So this syntax here where we say for, and then in parentheses, we've got a tuple where we've got 2 variable names. We've got airport code and airport name in airports, which is our dictionary. So the first guy here, airport code, is going to get assigned a key value, and airport name is going to get assigned the actual value. So here we're just looping through and we're printing out using string expansions the airport code and the airport name, which again you can see right there. If we wanted to iterate just the keys, we can use a property on the airports dictionary called keys. Same kind of a for in statement, but just with the keys this time. Likewise, we've got a property for the values that lets us iterate over all the values in the dictionary. So obviously in this particular iteration here, you have no idea which key these things are associated with. So that might not be particularly useful, but if you need it, you can do that. Okay, creating an empty dictionary. We saw one syntax up at the top to do that. Here is a sort of a more generalized syntax. I'm declaring a variable called dict. It's a dictionary with a key of type integer, a value of type string, and the default initializer syntax is just an opening and a closing parenthesis, no additional parameters required. And then I can start assigning values to it here. If I want to remove all of the elements from a dictionary instead of just a single element by key, I have 2 ways of doing that as well. I can use a range operator to say I want to remove all the elements within square brackets with just a colon there, and it will remove all the elements with a key that's in this open range. So that's basically all the elements. Or I can use a method called remove all, and I have a property that I can, or a parameter that I can pass in to remove all, which indicates whether I'd like the dictionary data structure to remove the elements and also deallocate the memory, or simply remove the elements but keep that area of memory allocated and ready for me to maybe insert some different values into the dictionary. So in this case, I'm saying I don't want to keep the capacity. So mutability of dictionaries is a little different than what we saw earlier last week with arrays. If I create a dictionary and assign it to a variable using let, this dictionary is immutable. It cannot change. So if I attempt to address one of the keys and change its value, I will get an error here. Swift tells me that it could not find an overload for subscript that accepts the supplied arguments. Basically, it's saying, hey, you've got a constant dictionary here. There is no overload for subscripting here that permits you to make this assignment. So that's different than what we saw with arrays, where you could actually still change the content of an array. All right, so now I'm going to set a couple of variables to point to that same dictionary. So, and this is going to kind of show us how copying occurs when you make assignments to variables. So both of these, dv1 and dv2, they're both pointing to that constant dictionary up here. And I can test initially whether or not they're the same, and in fact they are. So both of these variables are effectively pointers pointing to that constant dictionary. If I then take dv1 and I add a new value for the key thousands, and with the number 1000 in it, so what I've done basically is, I've got this dictionary in the variable dv1, and I've also got it in the variable dv2. And now I'm going to change something in dv1. So I add one new key value pair. And now I'm going to test the equality of dv1 and dv2. And you can see that now they are not the same anymore. Okay, so whereas for a brief moment, both of these pointed to the same constant dictionary, once I made this assignment to one of them and mutated it, the two dictionaries are no longer equivalent. And I can print the two out here, and you can see that the second one only has 3, and the first one has the thousands in it now that the other one didn't. So if I go back to dv1 now, and I remove thousands, then both of these dictionaries they're pointing to different bits of memory, but they are both, they're both going to contain the same set of name value pairs. So if I come back and I test equality again, now they're back to being true. They're actually equal to each other once again. And so here I print out the values of them. You can see that they're actually in different orders, right? The first one is 1, 10, 100, and the second one is 10, 101. But the equality operator still considers those to be the same because they contain the same set of name value pairs. Okay, so that's a pretty good sort of introduction to the dictionary. Are there any questions on the dictionary? Okay, let's move on now to, so for functions, we talked about functions during the first meetup. And I went through some very basic functions to show people how, I'm sorry, let me go back to this question. Someone just asked the question, what happens to dv1 to d1 after dv1 was augmented? Let's just go back in there and I'll show you. So d1 is a constant, and you can see that it's still 10, 100, 1. Even after this change here where dv1 got 1,000, at no point did this guy ever change. Okay? Swift made sure that this was a constant dictionary, just like you saw when we tried to uncomment this line here and it complained that it can't do it. There's no operation you can perform that will allow you to change this dictionary. Okay, so when we made these assignments, ultimately what happens is as soon as you start mutating them, it makes an entire copy of this dictionary, and the new variable points to that copy of the dictionary. Okay, all right, so we've seen some basic things about functions before, so some of this is going to be a review, so I'm going to go through it really quick, and then we'll slow down as we get to some of the more advanced stuff here. So the absolute basic function syntax looks like this, right? I have the keyword func, I have the name of a function, I have opening and closing parentheses, with, in this case, no parameters in it, and I am not returning any value, and I can do something in it. And this is how I would call it. Likewise, if I want to, I can pass in a couple of parameters, A and B. I declare the types of them, and I can do something with them. If I want to pass back a return value, I use the return arrow, which is this minus sign and a greater than sign combined together. And then I put the type of the return value. So this is different than other languages where you might be familiar with the return type being over on the left. Okay, and calling the function is the same, except for you can actually capture the return value into a variable or a constant. Another thing it can do is Swift allows you to return a tuple instead of a single value. So here I'm returning a tuple from a function with a status code and a status message. Imagine that we're doing some kind of HTTP operation, and then we can return our tuple. And then you can, again, you can capture that value into a variable, or in this case a constant, and then access the code and the message out of the tuple. And just to emphasize one thing about sort of the safety of Swift, if we comment that line out, So this is a function that only actually returns a value from one code path, right? If the flag is true, we're going to return something. Otherwise, nothing happens and we just fall off the end of the function. Swift will not allow this code to compile. They check at compile time to make sure that all control flow paths through your method return a value. So a certain class of error is just flat out avoided by doing that. Okay, so those are kind of the basics of functions that we saw before. So now we're going to get into some more advanced capabilities of functions that basically lay the foundation for us to start understanding closures. So the first thing here is external parameter names. The functions that we've seen up until now have all been of the basic form, you know, func distance and something like x1 double y1 double, that kind of a thing. Where effectively we give a name to a parameter and we give a type. Now this name is actually called the internal name of the parameter because this is the name by which you can refer to it inside the function. So I can say something like x1, you know, plus y1 or something like that. Z equals, right? Obviously it doesn't really make a whole lot of sense, but so I can access these guys using these internal names within the function. Now, if you're familiar with Objective-C, you know that in Objective-C, we have the concept of named parameters. The way a function is usually written in Objective-C looks something more like this, you know, like dist with x colon, you know, double x1 y colon double y1, right? A function name is kind of like this weird syntax where you have all these colons separating different parts of the parameter sets. And this part right here, and technically, effectively, this part right here, they are kind of the external names by which people refer to these properties. So when someone is calling a function in Objective-C, part of the syntax right there when they make the call to the function, it names the parameters that are being called. In Swift, a similar thing is possible using what are called external parameters. And so here, if we look at this function, distance between points, so the part we're familiar with is this part here, where we say x1 colon double. So that's a variable that's being passed in as a parameter, and its type is double. But here, before it, we've got another name separated by a space. And this name is the external name for that parameter. Likewise, over here for y1, the capital Y1 is external, there's another external, and there's another external. Once you have external names, then if we try and use the completion that's in Xcode here, you can see what's happening, right? Distance between points, parentheses, and it fills in x1 in caps, right? So if we tab over here, we put in something like 1.0 for the x1, 1.0 for y1, 5.0, 5.0. Okay, so those external names right there, the reason they are there is to help provide clarity in the code at the point where the function is being called. So it lets you remember that, oh yeah, the first parameter is the x component of the first point, the second one is the y component of the first point, and so on. Okay. If the person who wrote the function chose to define these external names, then when you call the function, you are required to use the external names. So once it's written like that, it's not possible to do this. Let me delete all this stuff here. Okay. That line, it doesn't know that function, okay? Because we defined these external names up here. We actually have to include them here as well. So that's invalid. You can't do that. Obviously, it's optional whether or not you want to include the external names at all. If you don't include them, then it's then you would call the function the same as we had seen earlier. Frequently, using these external names, you'll find the case is something similar to this, where the internal name and the external name are very close to one another, right? And if that is the case, Swift provides another syntax that allows us to avoid having to explicitly type in the external name. Another question someone just asked is whether or not the order of the parameters matters for an external names, and it does matter. This is not as flexible as some other languages where once you have named parameters, you can kind of mix and match the order in which you feel like providing them to the function call. That's not the case with Swift. You do have to put them in this order. Okay, so if we know that the external names are going to be something very similar to the internal names, but we feel like we really do want external names to be there, then they have a syntax where we can just write the internal name with a hash character in front of it, like this right here, hash x1, hash x2. And when we do that, then the external names become the same as the internal names. So it's lowercase x1, lowercase y1, lowercase x2, lowercase y2. Okay, so here again, because we have the hash, we have set this function up in such a way that it requires the caller to use external names. It's just that it was easier for us to write the function initially because we didn't have to write the names twice. Right? It's just a little bit more concise. Another thing that we have with Swift is we have the concept of default values for parameters. So here we've got a function called concatenate strings. We're passing in one string called S1 and one called S2. And then we're also passing in something called separator, which has an initial or default value of a single space. And this function returns another string. So basically the idea is we take S1 plus whatever the separator is plus S2, and we send that stuff back. Question is whether or not we can have multiple functions that share the same signature but different external names. And you can have function overloading in Swift, but I believe you have to actually have different sets of parameter types for them to overload. You couldn't have two functions that have the same name and each take two ints, but the ints have different external names. That isn't enough for the language to consider them overloaded functions. It would think they are a redeclaration of the same function, and it would be a compiler error. And I think we're going to get to function types in just a few minutes, and then that might make a little more sense. Okay, so we have our concatenation function here, and we can concatenate strings. So here I'm just concatenating my first and last name, and I'm not specifying a value for the default parameter here. So it uses the separator of a space, and the result is just my name with a space in there. If we want to use the optional parameter, the one that we specify the default for, we can do that, but notice that it has an external name, right? So it's called separator : and then has the value in it. If we use command completion here, you'll see that Xcode actually understands this default syntax. And when we do a concatenate, notice how it says we can fill in S1, boo, who, and we can put in something like that. Okay, but it knew that it had to have the external name for that property in order to know what it was. Okay, that's just part of the requirements of the language. If you're going to have something that has a default parameter value, then it's going to actually have an external name for the parameter. Okay, next thing we can look at here is the notion of variadic parameters. It is possible for us to pass into a function a a variable number of arguments, all of the same type. Excuse me. Sorry about that. So we've got this function called add numbers. Just a minute, please. Okay, we've got this function called add numbers, and it takes in a variable called numbers as a parameter, and the syntax for it is just the type followed by 3 dots. That indicates to Swift that 0 or more double values can be passed into this function, and we can access them as an array inside the function. So this function takes a variable number of doubles, adds them up, and returns the value. And you can see that inside the function we can use the for-in syntax to iterate over this full set of numbers, and then we can return the value back. When we go to call a function with a variable number of parameters, all we do is in parentheses just start writing in the values that we want, and that's all you have to do. Okay. So the next question here that we're going to look at is how do we actually refer to these parameters within the function, and what can we do with them? Let me check here. There's a question. Is it possible to specify 2 sets of variadic parameters back to back? No, it's not. You're only allowed to have one, and it has to be at the end of the set of parameters to the function. Yeah, so that's a limitation, but probably not all that big of a limitation, really. Okay, so if I want to, inside a function, refer to these internal parameter names and actually use them to do some sort of temporary calculations as I'm going through whatever my algorithm is, I might like to be able to do something like this: number equals number plus offset. Now, the default way that parameters are defined in a function, you can't do that, because these parameters, number colon int and offset colon int, those are effectively the equivalent of someone having said let number and let offset, meaning these are both constants. So those values are being passed into the function, but Swift knows you're not allowed to touch them. Okay, so I can't do this assignment here inside of the function. That's just not permitted. If I actually want to be able to do something like that, the language is, expressive enough to let us do that. So here's a similar version of that function, but this one works because instead of stating nothing about the variable, the mutability of the variable, I specify that I want this variable called number to be a var. And because it's a var, that means inside of the function I can actually adjust its value. I can treat it like a local variable. I can manipulate it. I can do things with it in the function. But I cannot pass that changed value out of the function. Okay, so it's genuinely a local variable scoped to the function. So here I've got a variable called n. I set it to a value of 10. I've got a constant called O, set it to a value of 2, so that's my number and my offset. I'm going to call the broken version with n and O. Obviously, that's commented out, so it really is doing nothing. So when I'm all done with this function call, the value of n is still 10, as we'd expect. I'm going to call the version that actually works now, where I can actually make a change inside the function. I pass in 10 and 2, and inside the function, notice it's 12. But when I come back here outside of the function, the value is back to being just 10. And that's because that change did not, escape outside of the scope of the function. Okay? So let or var are how you control whether you want to be able to treat a parameter as a local variable within a function. Going one step further, what you might want to do is you might want to actually have an input-output or basically a variable that's passed by reference, right? So here's a version of that same function, apply offset. But my intention with this version of it is that the number here, n, that this guy here is going to be allowed to be passed in with a certain value. And then after the function is done running, it's going to come back out of the function, but I'm going to have the changed value in my variable. And the offset is still a constant. Okay, so here it's the same thing, n equals n plus o. The syntax for passing in a in-out parameter is different. Notice how up here I just passed in the variable name n, even though it's a var, right? I just pass it in as n. But down here I have to use the syntax where I put an @ sign in front of it because I'm passing it in as an in-out variable. So the first version of this here, apply offset to number at n, is passing in a value for number, but it's using the default value for the offset. So it started out as 10, but after I return from that function call, it's now 15. I'm going to do it one more time here. I'm going to still pass in n by reference, and this time I'm going to also pass in a new value for offset. So now the returned value is 40. Okay, so that gives you an idea of how you can deal with these in-out variables. Okay, so now let's switch gears and talk a little bit about function typing. Basically, every function in Swift is actually its own unique data type. And the data type of a function is comprised of the types of all of the parameters of the function plus the return type of the function. So in the degenerate case of a function where you have a function that takes no parameters and does not return anything, Swift treats that as a function with this type. So open and close parens, return arrow, open and close parens. So it's basically saying a function that takes no parameters and returns nothing. Okay. So if you have a function that actually does take parameters and does return something, then the type is a little bit more interesting. Here I've got two functions. I've got an add function that takes two ints and returns an int. And then I've also got a multiplication function that has two ints going into it and an int returned. So these two functions have the same type. They are considered sort of type equivalent functions. And the type of the function is this: opening paren, int comma int, closing paren, return arrow, and then int. Okay, so that's the type. I can declare a variable of that type. Just like I can declare a variable of type int or double or string, I can declare a variable of type some kind of function. Okay, and so this is kind of the equivalent of what you might think about in C or C++ as being how I declare a function pointer. So here I'm declaring a variable called mathop, and its type is this: parentheses int comma int, close parentheses, return arrow, int. Okay? And now I'm going to take this variable mathop and I'm going to assign it the value mul. So I'm basically assigning mathop to point to this function. So this is a convenient way to basically hold a reference to some other function in your program that you might like to at some point call. And so here is an example now of actually calling it. So I have a constant called R1 that I'm setting up, and I'm calling whatever mathop points to, passing it the two parameters 2 and 3. And so you can see that it's multiplication right now. There's the answer of 6. So I can take that variable for mathop and I can reassign it to something different. In this case, I'm going to reassign it to the add function. And now I'm going to create a new constant, R2. I'm going to, again, just call mathop 2, 3 again, same thing, but this time it just did addition, and there's my value of 5. So like I said before, these are very similar to C function pointers. So since a function type is just a type, same as any other type, could you store a function in a let variable? Sure you could, yeah. You just wouldn't be able to change it, which may be exactly what you want to do. So that's kind of what we're doing right here in this thing. I have a function called perform mathop, and I'm passing in a mathop as the first parameter. So we know from what we talked about earlier that a parameter that's passed in is a let parameter, right? So we've got this math op. It's a constant thing. We can't change it. There's the type of the parameter that's being passed in. And then I'm passing in 2 more arguments for a and b. And so what this function is going to do is it's going to take whatever math op points to and call it, passing on a and b to it, get the result back, and then print that result out. So I can call perform math op. I just pass it add and the 2 variables, 2 values 2 and 3, and it'll perform the addition in this case. So you can see how we're starting to build up the capability to do things like pass a function pointer around to some other piece of code. And then that other piece of code could store that function pointer and call it at a later point in time, maybe as like a callback function or something like that. And so here is something similar where I have a function that returns some random math operation. So this is just to show you that just as you can pass in a parameter of a function type, you can also return a function type. So here we're returning a function of type int returns int. And we're going to use arc for random uniform to create a random number. We're either going to return add or multiply. Then down here, we're going to assign our math op to be one of those random things, and then we're going to go call it, same as we've done earlier. Last thing about functions, we can nest functions. So here I've got a function called sort numbers. I pass in an array of numbers to it, and I return from it a sorted array of numbers. Now, Swift provides a global function called sort, which takes 2 parameters. The first parameter is an array, and the second parameter is a function that adheres to a particular function type. And the function type is it has 2 parameters that are each of the same type as the values stored in the array, and that function must return a bool. So what I've done here is I've created a nested function called compare, which takes 2 ints in as its parameters and returns a bool. And then when I call the sort method, I just pass it the name of that nested function, and the sorting takes place. And then when I'm all done, I return the resulting array. And so here you can see I initialized a constant called numbers with my set of numbers. And then I call sort numbers, and sure enough, they started out in descending order and now they're in ascending order. Okay, so that's a little sample of what you could do using nested functions. Any questions about what we've seen about functions or function types? All right, let's see how far we can get on closures. Not sure what your question refers to about tail recursion exactly. Are you asking about how? I'm actually not sure about that. Okay, let's take a look at closures. So the reason why we just spend all that time talking through what functions and function types do is because closures are basically function types. So according to Apple's definition, as you can see here on the screen, closures are self-contained blocks of functionality that can be passed around and used in your code. So we'll get to this capturing and storing of references thing in a minute here, but basically the whole idea behind a closure is you create some little self-contained block of code that you want to be able to hand off to some other part of your application so that it can use it. It turns out that there are 3 ways in which closures can be constructed. They can be constructed as global functions, they can be constructed as local functions, or they can be constructed as what are called anonymous closures. They're all basically the same. They all basically look like a function type, just like what we've been seeing. So in essence, this thing at the bottom here, this function that was passed into sort was a closure. Okay, so we've got a set of examples here about closures. We're going to start with an array of names, and we're going to define some various things we can do with closures. The simplest thing is we can create a global function. Looks just like the things we saw in the previous playground. So we're creating a function called backwards that takes two strings and returns a bool. So that matches the type that the sort function expects the closure to adhere to. So we call this sort function, we pass in the names, we get back our reversed set. So that's sort of the simplest way where we explicitly define the closure as a separate function. There is a closure expression syntax that allows us to inline the closure definition with our function call. And the general form of this is we start with an opening curly brace, and then we define the set of parameters that we expect to be passed into the closure, and then we specify the return arrow, and then we specify the return type. And so effectively, this whole section right here, that is the type of the closure, right? That's the same as a function type that we just looked at previously. So you start with the opening curly brace, you put in the type of the closure, then you put in the keyword in, and then you put some number of statements that are the actual logic you want to be performed in that closure, and then you close it off with a closing curly brace. So here's that same sort function, but this time instead of referring to the global function backwards, we're putting the same logic right in line. So we're saying sort parentheses names, comma, and then we start defining the closure with that opening curly brace, and then we define the full type of the closure here, and then we say use the keyword in, and then we define the actual logic for what needs to happen inside that closure, and then closing curly brace, and then the closing parent. So this whole section right there that I have highlighted, that is the closure parameter that's being passed into the sort function. So this is a convenient way to write the closure, very similar in many ways to the block syntax in Objective-C. But the folks that built Swift thought this could be made even more simple and concise by removing some of the obvious things in this sequence of syntax here, because there's some things that it already knows. The language already knows that the sort function expects the second parameter to adhere to this particular type. So the first thing that we can do is we can actually take that whole thing away. And as you see here, we can just put in the list of parameters, S1 and S2, and then still the in keyword and then our return. So this is exactly equivalent to the earlier one up above, except for it's just more concise. So we can even go a little bit further than that. We can say, well, actually, since it's only a single statement that is being evaluated inside the closure, we can take away the return statement as well. Okay, so that return statement is kind of not really useful. So we can write the closure as S1, S2 in, and then the logical expression that should be evaluated, and the returned bool for that expression is what the closure will return. So that's getting better. Now we can go even one step further. Instead of having to name these two arguments, Swift provides positional shorthands for the arguments to the closure. So this is again the same thing that we saw above, except for here we're using Swift's syntax for positional arguments to say $0 greater than $1. So basically we've just replaced that whole portion right there with a decision to use the positional arguments instead of the named arguments. So this is the same closure again. And this one's kind of odd, but we can actually even go one step further. The string class has a method on it for the greater than operator. So the greater than operator is an overridden function inside the string class. And that overridden function happens to adhere to this particular function type, which matches exactly the type that is expected by the closure. So believe it or not, this right here is the same thing as this one up here, and so on, right? So it's extremely concise. I'm not so sure this is really the best practice to write it like this, but the language permits it, and the language will resolve what that means and which function should get called as the closure. Okay. One more improvement to it is very frequently you will be writing functions, or you will see functions in UIKit where the function takes a single block or a single closure as the final parameter of the function call. And as a result of that, you'll often write code like the sort function here, where you've got these curly braces for the closure right near the end, and then you've got the closing parenthesis from, you know, the function call, which really started much earlier in your code. So imagine a closure that is multiple lines of code long, multiple expressions. A syntax that they allow is for you to move this parenthesis to the other side of the closure. So here we're saying sort opening paren names closing paren, and then we put the closure after it. Now this syntax only works if the closure is the last parameter to the function you are trying to call. But in that case, this syntax reads much nicer. It reads much more kind of like a control flow, where you're calling sort with this parameter, and then this is the closure that's going to get run. Okay. So one other thing that closures can do is they can do what's called capturing of values. And the basic idea here is that if I express some logic in a closure, sometimes what's in that closure may want to manipulate or just have access to variables that are part of the surrounding context. So here is a function called makeIncrementer, which takes a named argument called forIncrement of some amount. So basically it's saying, create me a function, because if you notice, the type that it actually returns is a function that takes no arguments but returns an int. So I want to make an incrementer. So I want to create a closure or a function that knows how to increment by some certain amount. So I have a variable here that's locally scoped to my makeIncrementer function. It's called running total. And then inside there, I have a nested function, which is basically a closure, called incrementer. Incrementer takes no parameters, takes no parameters and returns an int. So you can see that this type matches the returned type for my makeIncrementer function. Now what this function does, though, is it actually changes the value of the running total. It says running total plus equals amount, and then it returns the new running total. So in essence, this function is reaching outside of its scope into the parent scope here, and it's interacting with this running total, which all seems fine as long as we're inside this function. But remember that our function is actually returning a closure so someone else can call it later on. So in essence, by the time we get here to this return statement, right, when we return, the stack, the variable that's on the stack for running total goes away, right? The stack frame is gone for makeIncrementer. But since we have this closure here, and since closures do what's called capturing of values, it actually captures this value and copies it someplace on the heap where it can interact with it later on. Okay, and so that's a very powerful construct that you make use of with closures. So now here we're actually going to use our makeIncrementer. We're going to create a constant called increment by 10. And so we're calling makeIncrementer for an increment by the value of 10. So all this did was it returned for us if I click on that there, you can see what it returned is a constant called increment by 10, which takes no parameters and returns an int, just what we expect. So now we've got this function and we can call it increment by 10, and you can see that our value, which started out as a 0, is now 10. And then if we call increment by 10 again, the value is now 20. Okay. The thing to keep in mind here is that these calls are interacting with a captured copy of the running total variable that lives on the heap. It's not the version of the variable that lives on the stack or that lived on the stack. So now here I can create yet another make incrementer. This time I'm going to make one that knows how to increment by 7, and I'm going to call it. And so you can see that it's changing something different. When I called make incrementer, it entered this function, which has a local variable called running total, which is getting assigned the value of 0. And then the closure captured that running total. So it initially captured 0 and stuck it on the heap somewhere and did the increment by 7. So when I actually call increment by 7, my answer is 7, not 27, right? If capturing didn't work the way I just described, more than likely we would have ended up with a result here that we didn't really want. So now if I go back and I call my increment by 10 again, you can see that it's actually incrementing that 20 from last time, and now that's 30. So this last little bit here on closures, I think is kind of obvious about how reference types work, I think. So since we have a function type called increment by 10, we can actually assign another variable to store the same thing. And through the type inference in Swift, this other variable, another incrementer, also becomes a closure that is taking no parameters in and returning an int. So it's the same type. And if I call this thing through another incrementer, you can see that its value is 40. It's not like it became 10 because it was a copy of it or something. It's literally a reference to the same thing. Okay. Let's see. So we're at the 1 hour mark. So I think we'll hold off on enumerations until next time. So let me open it up to questions now. If anybody has questions on the closures or anything that we've seen up to this point. So if nobody has any questions right now, oh, here come the questions. I guess I'm not patient enough. Okay, let's see here. First question, do closures suck up values from variables outside the function scope as well? I believe the answer is yes. Not just the immediate scope around it, but anything all the way up to global scope. All right. I'm wondering whether the return operator can be used with parentheses to express a particular complex type, like a function that returns a function that returns a function. I don't know. I haven't tried it. I'm not sure whether you can override the function return operator or not. I haven't really played around enough with the function overloading or the operator overloading to know. Yeah, it's an interesting question, but I'm not sure I have an answer for you right now. All right, well, I want to thank everyone for joining me today. I will put a recording of this out as well. And Look for another one to be announced on the meetup soon. Oh, there's one more question here. How come the playground has X times in the results? Where does, so this is how many, so in this playground here, how many times has this particular thing been invoked? So this is just saying how many times, in this case, it's how many times has sort been called, I believe. So sort has been called 5 times in this particular playground. And we've come through this return incrementer twice because we did it once for the incrementer with 10 and once for the incrementer with 7. So it's kind of like that. It's kind of showing you just sort of how many times you've gone through different parts of the code. Because I guess in the playground, you might be seeing something unexpected there. Like I expected it to only go through this once, but it says 10 times or something like that. All right, so I think we'll wrap it up there. Thank you all very much, and hopefully I'll see you at the next one. Bye for now.